Today we know what the atom is. For example, if I think about, say, an atom of carbon, we know that in this atom it has a nucleus and it has electrons around it. Now, let's see. We know that in the nucleus of carbon there are 1, 2, 3, 4, 5, 6 protons in the nucleus. We know that there are 6 neutrons. 1, 2, 3, 4, 5, 6 neutrons. We know that there are 6 electrons going around the atoms. So 1, 2, 3, 4, 5, 6. So we know all these details, and these electrons are going around the atoms. So we know quite a lot about something that is so tiny, something that's about has a size of about only 10 to the power minus 10 of a meter. And these right, so those are the electrons. Okay, so these are the electrons, and we have the neutrons inside, and we have protons inside. Okay. Now I'm just going to quickly summarize some of the data, some of the numbers and words that we would use quite a lot in this topic on nuclear physics. So starting with the atomic number. Atomic number. Now the atomic number is often represented by the symbol Z, and it is equal to the number of protons. The number of protons in the nucleus. And the other thing is the idea of the mass of the electron and the mass of the protons and the mass of the neutrons. Now so in the case of carbon, let's say there are actually 6 protons. There are 6 neutrons, and there are 6 protons, and there are 6 electrons. Okay, and we would represent this information using a symbol C to stand for the element carbon, and we would write the number of protons or atomic number as a number on just in front of the letter and just under the letter itself. So, and we would write the total number of protons and neutrons as a small number on top here, which is 12. Okay, so we call that number the mass number. the mass number. We might sometimes see the letter A used to represent that. So this would be the number of protons plus neutrons. Okay, so that's the mass number, and right, so that's the symbol that we would see quite a lot in nuclear physics. Apart from that, other information that that we would often have to use would be, say, the masses of these particles, of these protons and neutrons. Now, because the mass is so small, it is not convenient to use units of kilogram to represent that. So it is often expressed in terms of something called the atomic mass unit. Now, the atomic mass unit is a number often represented by the symbol U, which is equal to 1.66 times 10 to the power of minus 27 kilogram. A tiny number. It's represented by U. Sometimes it's also written as M with a subscript U. Okay. And the mass of a proton and the mass of a neutron is very nearly equal to U. So I emphasize that it is very nearly, but not exactly, and we'll see why it's not exactly in a later video. Okay. So, but what I'll do is I'll just write down this understanding. Okay, that this is roughly equal to the mass of a proton, which is often written as mp, the mass of a neutron. Okay, so this is proton, mass for proton, and mass for neutron. And the mass of an electron is a lot smaller than any of these. Before that, let me quickly say where this number comes from. It seems like a number that just appears for no reason. 1.66. Why 1.66 and why 10 to the minus 27? And why is it actually not exactly equal to either the proton or the neutron's mass? Okay. So while I answer the why not exactly equal question later on, I can say quite quickly that this number is actually equal to U is equal to 1 over 12 times the mass of this atom, this carbon, what is called a carbon 12 atom. Okay, and the reason why I say carbon 12 and not just carbon atom is because it's actually possible for carbon atom to have a different number of neutrons. Carbon atoms must always have 6 protons each, but it's possible for the carbon atom to have maybe 7 or 8 neutrons. That's possible. So in order and if there's more neutrons, obviously it would be heavier. Mass would be different. So that's why I need to specify that it's a carbon 12 atom. And if you see the word carbon 12 atom, we know that because there must always be 6 protons in a carbon atom, we would know that there are only 6 neutrons. So it's 1 over 12 the mass of a carbon 12 atom. Now, why is it 1 over 12 the mass of a carbon 12 atom? Why not a different atom? And why 1 over 12? Well, 1 over 12 because it's very nearly equal to the mass of a proton. But why not the other atom is complicated and maybe historical question. So I shall not try and answer that. I don't really know either. But for now, alright, let's just know about this and go on to see how we could use this knowledge. Okay. Now, what I like to do next is to say a little bit more about how we would use these symbols in nuclear physics. And these symbols are normally used in say nuclear reactions. So just to give a few examples, just to give a few examples. Now, if we take a nitrogen gas, I would write the symbol of the nitrogen atom like that. So from what I described just now, this means that the nitrogen atom, which is represented by this capital N, has 7 protons, and it has a total of 14 protons and neutrons, which means that it has 14 minus 7 neutrons. That is 7 neutrons. So it is known that if you take a bottle of nitrogen gas and you shoot it with alpha particles, and it's also known that alpha particles are actually the same as the nuclei of the helium atom, which has each of the helium nucleus has 2 protons and 2 neutrons. So the symbol would be 2 and 4. So it's known that if I shoot this nitrogen gas with alpha particles coming out from some radioactive source, then it would produce oxygen. It would produce oxygen gas and hydrogen. Now oxygen has 8. That's oxygen. Oxygen has 8 protons and let's see. Oxygen normally have 8 protons and 8 neutrons, but some oxygen, a small fraction of oxygen atoms might have 1 extra neutron, and in this case the product of this reaction has actually 9 neutrons. That's why we have a 17 up here. And for the hydrogen gas, in this case, the hydrogen nucleus that is produced by this reaction has 1 proton, just 1 proton and no neutron. So it's just 1 and 1. So this is a possible nuclear reaction that can happen. And as you've seen, this is how we can use a symbol. Now, if you look at this symbol, if you're seeing this for the first time, it can be confusing, not only because there are so many different symbols, because there are so many different numbers. Okay, but let's try and find some order, some way to understand the relation between these numbers a bit better. Well, let's start by looking at the numbers at the bottom. Okay, you see, I have a 2 here and a 7 here on the left. I have an 8 and a 1 here on the right. 2 plus 7, or 2 and 7 are the proton numbers. So that means that there are altogether 9 protons. Right? 2 plus 7 is 2 plus 7 protons in the beginning, and after the reaction, after shooting these alpha particles at the nitrogen atoms, this a nuclear reaction takes place, and these are produced. Then in the product, right, for each pair of these produced, there are 8 protons here and 1 proton there. So 8 plus 1 protons. But you see, 2 plus 7 is equal to 8 plus 1. They're both equal to 9. And this tells us that the total number of protons has not changed, even though the elements have changed. Like nitrogen has turned into oxygen. Helium and nitrogen has turned into oxygen and hydrogen. So even though the elements have changed into something completely different, right? Obviously nitrogen is different from oxygen. We have to breathe in oxygen, and oxygen can support burning. But something hasn't changed. The number of protons has not changed. And in this case, as it turns out, the mass number also has not changed. So the mass number, okay, which is the total number of protons and neutrons, you'll find 4 plus 14 for this so-called nuclides. Okay, we describe this as nuclides. I'll define the term in a moment. And the total mass number after the reaction is 17 plus 1. And you see that 17 plus 1 is actually equal to 4 plus 4, 14, right? 4 plus 14. So the mass number has not changed. Okay. So this gives us some kind of rule or order in this reaction, so that we can use this to at least understand a nuclear equation to some extent. So for this video, let me finish off with writing down one more term, the term nuclide. Now I've been using the word nucleus quite a lot up to now, and you know what nucleus means. It's the center of the atom. It is that lump, or that lump of mass of protons and neutrons, right? With the protons and neutrons. Now, but what do we mean by a nuclide? Well, now as I described just now, say for nitrogen or for carbon or even oxygen, it's possible for nucleus of the same element to have different number of neutrons, right? For example, an oxygen must always have 8 protons, but it can have maybe 16 neutrons or 17 or 18 even. Okay, so when we just say the nucleus of oxygen atom, for example, all we know is that it must have 8 protons, but we won't know whether it has 16 or 17 or how many neutrons exactly. Okay, so nucleus, the term nucleus of an atom would say when we say the nucleus of an oxygen atom, all we know is that it has 8 protons, but we don't know how many neutrons. But if we say nuclei of an oxygen atom, then we must specify, or we are referring to a specific number of neutrons as well. So this refers to a specific number of protons and neutrons. If you just say nucleus, alright, that means only this has to be specified. Now, I think this description is kind of okay if you're familiar with how to use these terms, but if you're seeing this for the first time, it's probably still a bit abstract. So let me just really clarify this with an example. So if I'm just going to say nucleus, let's say I say nucleus of oxygen atom. Okay, so if I just say nucleus of oxygen atom, what does it mean? And so if I just say nucleus of oxygen atom, it means that I know this nucleus has 8 protons. I know this nucleus has 8 protons, but I don't know how many neutrons it has. So 8 protons, unknown number of neutrons. Now, if you're familiar with oxygen nuclei, you know that number can be 16 would be the most abundant kind of oxygen nuclei that occurs in nature, but there could also be a tiny amount of oxygen nuclei that have 16 is the total actually. 8 is the number of neutrons that is most common in oxygen atoms, but there might also be maybe 9 or even 10. So there are a few possibilities. Okay, so we are not sure. We wouldn't be sure if you just say nucleus of an oxygen atom. We won't know what these numbers are. But on the other hand, if I talk about nuclide of an oxygen atom, right, if I say nuclide of an oxygen atom, then I must specify both this and the mass number, or the number of neutrons. Okay, so if you're given the nuclide of an oxygen atom, that means you're given both of this information, and you would know that there are, in this example, you would know that there are 8 protons and there are 17 minus 8, which is 9 neutrons. So I hope this gives a clearer idea as to the difference between, or different ways to use the word nucleus and nuclide. So this also means that a nucleus, since a nucleus can have different possible number of neutrons, it means that it is possible for a nucleus of an atom to have a few different nuclei. So apart from this one, the other examples would be maybe all 16 or O 18. So oxygen might have these 3 or even more possible nuclei.